then officially start. All right, welcome to the DDPS seminar, everyone. Before we introduce our invited speakers, let's go over some rules and logistics as usual. First of all, please mute yourself during the talk unless you have questions. If you do have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences, and therefore no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Igor Mezic, who is a distinguished professor at the University of California, Santa Barbara. He pursues research in the fields of artificial intelligence, dynamical systems, control theory, and applications to security, energy-efficient design, and operations in complex systems. He did his PhD in dynamical systems in Caltech. Dr. Mezic was a postdoctoral researcher at the Mathematics Institute, University of Warwick in UK. From 1994 to 95. And from 1995 to 1999, he was a member of College of Engineering at the UC Santa Barbara. From 2000 to 2001, he has worked as an associate professor at Harvard University in the Division of Engineering and Applied Sciences. He won numerous awards. Just to name a few, he won the Alfred Sloan Fellowship, an NSF Career Award, and George Alex XB Outstanding Paper Award from IEEE. He also won the United Technology Senior Vice President for Science and Technology Special Achievement Prize in 2007, and many more. Dr. Mezic is the director of the Center for Energy Efficient Design and head of Buildings and Design Solutions Group at the Institute for Energy Efficiency at the UC Santa Barbara. He holds 10 US patents. He founded AIMDyn in 2003 and is the CTO and chief scientist of Mixed Mode AI. Today, Igor will talk about Kukman operator theory, which is really popular these days, for dynamical systems control and data analytics, which is a very interesting topic. Now, without further ado, let me pass the baton to Igor by asking one question as usual. Today's question is, what is your favorite thing to do other than research?
That's an easy question, Yangsu. Music.
Oh, music? Oh.
Yeah.
Do you compose music or play music or?
All of it. I was brought up in a musical family, and my mom taught me instruments when I was very young, so I kept it as a passion all my life. Guitar mostly, but some piano as well.
Guitar and
other instruments. I cannot play any wind instruments. Those are too hard.
I see. Well, someday I want to hear that in person. Okay, it's all yours. The stage is all yours.
All right. Well, first of all, thanks very much for this invitation. It's a pleasure to talk here. I've been to Lawrence Livermore once in the past, and it was fun. A couple of days of discussion. It was a long time ago, so I'm happy to be back. I'll talk today about Koopman operator theory in general, but I'd like to point out, a few things that are happening these days. As Yangsu pointed out, it's becoming a pretty large field. I think there are two directions that are becoming really, really interesting in this context, and I'd like to emphasize them. One of them is in the direction of control, expansions in direction of control theory. And the other one is expansion in context of learning. And I'd like to advocate that for dynamical processes, this provides us with a very nice framework for learning. So I'll try to show you examples of that. Let me see if I can move. Okay, so let me speak briefly about sort of the core aspects. Koopman operator theory is a reformulation of dynamical systems theory that stems from Poincaré's work, originally dynamical systems theory. It's a reformulation in terms of evolution of observables. I'll go through this in some detail. Koopman and von Neumann used it to study measure preserving systems. In mathematics, you're going to find the Koopman operator named the composition operator. Actually, it predates Koopman as far as the definition is concerned as the composition operator. There is something that's called a Schaefer equation that is in effect an equation that describes the action of the Koopman operator. The starting interest in this was the spectral analysis. You will see that the operator is linear, and so any self-respecting scientist or mathematician, when they see a linear operator or a matrix, they go for its spectra, eigenvalues and eigenvectors, in this case they're eigenfunctions. The operators are non-self-adjoint though, so this comes from quantum mechanics, but in quantum mechanics you have the inspiration for this was quantum mechanics, but quantum mechanics usually deals with self-adjoint operators. But in dynamical systems, this helps us to unravel the state space geometry. And originally I thought about it as a way of enabling model reduction as well. But it's proven also, as to a certain extent I suspected early on, that linear control methods can be used for controlling high dimensional systems that are nonlinear, in fact. So this combination of model reduction and control, I think, is these days becoming very interesting. And then also the relationship to data analysis is very direct. So as opposed to geometrical theories, which the analysis is data analysis is harder from that perspective, because essentially the numerical methods are algebraic. The relationship to data analysis is very organic, and so in that sense it's similar to stochastic process theory. Actually, sometimes I refer to it as basically non-stationary stochastic process theory. Let's see further. So what was the focus in the last, let's say, 20 years? The focus has really been away from the original Koopman and von Neumann ideas to dissipative and hybrid systems, because they originally considered only conservative systems, think Hamiltonian systems. We have a lot of high dimensional applications, power grids, fluids, building dynamics that I'm actually quite interested in myself, molecular dynamics. I'm going to show you today an interesting application which we did with DARPA support, which is game dynamics. And then network security, there is really, Mixmode.ai is a company that actually has taken these types of ideas and applied them in network security successfully. So a pretty broad range of applications. It's a uniform mathematical framework for both random stochastic dynamical systems, hybrid dynamical systems, and deterministic. So it doesn't really stay within the realm strictly of deterministic dynamical systems that Kukman and von Neumann, deterministic Hamiltonian dynamical systems that Kukman and von Neumann envisioned. We've gone pretty far beyond it. And then I think the most interesting type of application today is in learning and AI. And so I'll show you some examples of that and tell you how, what are the differentiating factors there. On the left, what you're seeing is an original application where what you're looking at is the streamwise component of a flow getting out of a circular orifice. This is used for example, cooling jet engines, where the flow out of jet engine is going in this direction. So there is a cross flow, and this jet is coming out. Think of it as also smoke coming out of the chimney, but it's really a cooling of a jet engine application. And so the purpose of this movie is to show you this. It looks like very much a random dynamical process, but it turns out that if you find eigenvalues of this operator, that I mentioned, that you end up having, so here are these bright dots, blue and red, are actually eigenvalues. You end up finding structures that look very, very coherent in this messy flow. So that's kind of the basic idea, and I'll tell you a little bit more about the splitting, about the coherent and non-coherent part of the dynamics as we go. So another little part of introduction is here. Originally, dynamical systems were taught in the context of ordinary differential equations. This is kind of a Newton's point of view. And if one is lucky, and in particular, if we have a simple enough system, in this case, mass spring system, one can solve the equations analytically. Now, of course, in general, this is not possible. That led to the whole evolution in chaos theory, revolution in chaos theory. Many ordinary differential equations, even in 3D, don't have explicit closed form solutions. So what Poincaré introduced is this picture of state versus state rather than state versus time. And so that led to whole dynamical system geometric theory. But there is a third point of view, which is spectral, that Wiener introduced, well, you could go all the way to Fourier, of course, back, but Wiener introduced during the Second World War and after that. And a really interesting aspect of this that plays with the Koopman operator theory is that there is a single plot here in the power spectral density. So here is the frequency, here is the amplitude of the power. If there is a single line, we immediately know that if we know that particular frequency, omega n, and if we know the amplitude and phase of the evolution, we can reconstruct the signal. So if you wish to look at the first encoder in the history of machine learning, it's right here. That's how I like to look at it. Now, Koopman-von Neumann were interested in the following idea. Yx, position and momentum, for example, for dynamical systems. Energy, of course, is a really important observable, and yet the primitive equations are not written in terms of energy. So why not ask, what is the general evolution for any arbitrary observable, and then try to find the ones that are better, or rather simpler, in describing the motion than maybe your original ones. Energy is a particular example here. If we were to write an equation of evolution for energy in this system, it would be just E dot is equal to 0. The energy doesn't change for the mass spring system without damping. So they wrote a formalism for conservative systems or Hamiltonian systems that extended that and basically wrote down an operator that I'm going to describe next. So the idea is, suppose you have an observable on the state space M, and you have a mapping. This is a discrete time mapping. Here is a continuous time mapping. This would be a solution of an ordinary differential equation. Then if you compose the observable F with the mapping and say that's a new function of X, then you can say, well, I took a function F and I produced a new function. And it's easy to see that that operation is linear. Just put F1 plus F2 here, the composition ports through, and you see that the operation is linear. So U itself is a linear operator of composition with a map. Here in continuous time, it's a composition with the flow. So that's the idea. It originally appeared in 31 and 32. Karleman was, some of you might know about Karleman linearization. Karleman was second to arrive at this idea. Koopman was first. Karleman was aware of this and pointed out that someone told him that Koopman already had that particular idea before. To remove a little bit of mystique, if you have a x dot is equal to f of x, for those of you that know advection equation in fluids, the generator for these evolutions is actually an advection equation with a kind of wrong sign. So if you ported this to the left-hand side, there would be a minus here. So it's a forward-looking rather than a backwards-looking equation. Why is that? Because this composition says if I'm at point X, I go forward one step, and I looked at the value of f at that forward step, and then I bring it back. Right? It's a pullback operation, while the usual advection equation looks at what's coming in, what kind of densities are coming in. That's the duality. And then again, that's a linear operator, or this is a linear family of operators. So you can ask, what are the eigenfunctions in this case? And if you work from the generator side, then you say, okay, if we assume that this evolves as e to the lambda t in time, this should remind you a little bit of quantum mechanics, then this is the equation that phi and lambda need to satisfy in order to be eigenfunction and eigenvalue for this equation. On the operator side, it just says that the evolution of phi, this particular observable, so now we chose one, is e to the lambda t phi of x. So spatially, the observable doesn't change, its amplitude changes. So eigenfunctions are special functions, simple functions, and their evolution is basically governed by linear equations, because this thing on the left is really phi dot. So the equation for an eigenfunction is phi dot is lambda phi. This is why it's often said, or rather it should be said, usually it's said that Koopman operator is a global linearization tool. But what is more important in my view is that it provides you with finite dimensional reduction to a linear system. If you find phi, even for a non-linear system, this is going to give you a representation of the evolution of that function, even for a one-dimensional evolution that is very simple and linear. So the methodology is capable in certain cases of producing finite dimensional linear equivalents of nonlinear systems using special observables like eigenfunctions. What do we get out of that? Well, part of it is geometry of level sets of Koopman eigenfunctions in state space, and then if we do projections of vector valued observables, they are going to give us Koopman modes. And in general, very often you don't necessarily want to exhibit the operator, and you'd like to get eigenfunctions directly from data without really representing the operator. Representing the operator might be a hard thing to do. And I'll talk about it in the next slide as to how you can. But some of my original work was dealing with finding eigenfunctions and eigenvalues directly from data without exhibiting the operator. And the nice thing about the Koopman operator formalism is that this is actually possible. You don't need to know what the operator is in order to construct its eigenfunctions directly from evolution. If that sounds strange and magical, it actually isn't. You don't need to know a matrix in order to find its eigenvector. If its eigenvector is, for example, coinciding with a positive real eigenvalue, then it's enough to know the evolution of an arbitrary vector because it's going to align with that eigenvector over a long time. And it's enough to rescale the final result in order to get an eigenvector. So in the same sense, although much trickier because the Koopman spectrum is usually contained within the unit circle and within the unit circle. That means that you have oscillatory dynamics, and this example that I gave of a matrix cannot be ported in a simple way. But that's exactly where some of the methodology sits. So I won't say much more about this. If anybody's interested in the methodologies of finding the spectra and eigenfunctions directly from data without exhibiting the operator, happy to talk about it after the talk. But let's talk briefly about what does it mean to actually exhibit the operator. I have an abstract point P, and then you have, let's say, P prime, which is the next point that the dynamics in the state space takes you to. And let's say that you decided to describe that evolution by some set of functions that we labeled by boldface x. So the x prime, which is the x associated with P prime, is some nonlinear mapping of x, let's say. Let's say we have a closed set of equations. As I said, these might be positions and momenta, and we might decide that we instead would like to use some other functions to describe the evolution. So let's say we produce a basis of functions, fj, on this state space. then we can represent the original states as a sum over some coefficients times fj. And here is the space that we embed it into. So these observables live in their own space, and so we have a point in that space. Now let's act with u on an individual basis function. So u fj, in many cases, if you choose an appropriate space for operation of u, can be represented essentially as a matrix. These are again basis functions, and this is djk. So that's the coefficient describes the kth coefficient of function fj in the frame fk. So now applying u to this whole x, you will act on each fj, and so one is going to get the following expression. It's just djk multiplying cj's, which are the coefficients of the original state. And so now you see that that's basically a matrix operation. So the Koopman operator now becomes this matrix djk, and you multiply that with coefficient cj, and you get x prime that describes p prime, really. So that's what it means to exhibit the operator in some basis. And you can see that this nonlinear, potentially nonlinear dynamics is represented entirely linearly here, right, as a matrix operation. So that's one of the new things that happened in the last, let's say, 20 years or so, maybe 20, 30 years or so, that we realized that we can, do some applied mathematics, I would say applied mathematics for this operator in the context that we approximate it in a certain basis. So let's go back a little bit and say, okay, if you have that representation and you have an observable G, one of the ideas here is I could utilize the eigenfunctions to understand how different parts of the systems interact. And that expansion is now called the Kukman mode decomposition. So if you take an arbitrary vector observables G that are functions of Z, that's a field variable. Let's say you're looking at a fluid flow, this would be a point in space, and then X, which is a state space variable. Then it can be split into the time average, which is the G star that depends on this field variable. And then some components that grow, decay, or oscillate exponentially, so complex exponentials, obviously, multiplied by an eigenfunction. And then this projection is really a projection onto Koopman modes that, as I said, you can actually do directly from data without integrating over a very high dimensional space. That's one of the tricks that is very useful. But then you have this part, and that's the part that is the continuous spectrum. If you have chaotic dynamics in your system or noise, there is going to be continuous spectrum. Very often in computational work today, this is neglected. It really shouldn't be. There are a few theoretical works that have appeared recently that treat it and provide also numerical methods. But one of the ways you can look at this decomposition into the time average, growing, decaying, oscillating modes, and continuous spectrum is really a decomposition of dynamics into coherent parts and continuous spectrum parts, or call it, if you wish, noisy, but that includes chaotic dynamics as well. So examples of this is what I've shown you at the beginning. These modes here, SJs are modes, phi j's are eigenfunctions. So there is this triple: eigenvalues, modes, eigenfunctions. So these shapes that are associated with that jet, when you sum up over these and a bunch of other stuff that includes some continuous spectrum, you actually get back the whole dynamics of the jet. So if you pick up these eigenvalues here, they correspond to the slower evolution, this is this mode, and faster evolution, that is that mode. So those are just some. But of course, you see many more objects here, and then you see this pale stuff in the spectrum, and that is really the continuous spectrum part. Now, you can play this game in a large variety of applications. I'm pulling out some that we've been associated with. We've designed, or rather utilized these methods for building energy efficiency. For example, this gives you a mode that reflects the temperature evolution in a room over a 24-hour time scale. So it's a daily period mode. Power grids, I'll show you some examples of that as we go. This is a picture, a heat map of a 24-hour mode of a network. On the horizontal axis, there is IPs labeled as just numbers. And then on the vertical axis, the same set of IPs. And if you're seeing red in this mode that is plotted as a heat map, that means that that pair, this IP and that IP, are corresponding perhaps during the daily office hours, 9 to 6, and then are shutting down during the nighttime. As you might imagine, if you don't see any, if on some days you see this happening and then suddenly they're chatting all the time, there might be actually a problem. So you can see how this could potentially be applied to security. And if you're interested in how this is applied in the context of network security, look up the website there. It's kind of an interesting application that really works on the basis of what I mentioned, and that is the spectral analysis, where you don't need to necessarily exhibit the operator. All right, so let's talk a little bit about eigenfunctions, because I want to give you an impression of the mathematical properties of these eigenfunctions, because at this point you could ask yourself, well, this is an infinite expansion in principle. K can go to infinity. So isn't this, very complex? I'd say potentially, but of course we do basis expansions in many different contexts. So we cut off at a finite size. The Koopman operator provides us with something better. It actually provides us with the ability to get an infinite number of eigenfunctions from a finite one. But for that, I need to go into a little bit of theory. So the eigenfunctions of the Koopman operator have really nice algebraic properties. Namely, what this proposition tells you is that if you're in a particularly defined space, so it's a vector space closed under pointwise products of functions, so it's an algebra, and then you have a constant function in it. The constant function needs to be there all the time. That's kind of a trivial requirement. Then the set of eigenfunctions forms what is called an abelian monoid. What this really means is that if you have two eigenfunctions in that space, then their product is an eigenfunction as well. So that's useful. That's quite useful. The reason being that, let's say you have linear systems in which geometric multiplicity is equal to algebraic multiplicity. I don't know why this is sitting here. You can explicitly find the eigenfunctions as inner products of X with the left eigenvectors of A. You can find explicitly an expansion for a linear system. Here are the eigenfunctions. Here are the eigenvalues. They're really Koopman eigenvalues are now the eigenvalues of the matrix as well. And here are the modes. They're familiar notions. They're eigenvectors. So you see, in this case, the expansion is finite. So if you have a linear system on a linear space of observables, so only the states themselves and the span of these equations describing observables describing the state, then the expansion is finite. And you can do a variety of things. If you're interested in dynamical systems, then instead of looking at eigenvectors, you can look at eigenfunctions as geometrical objects in order to understand the state space. But interestingly, even if you go to the nonlinear case, in particular, the first nonlinear case that you can think of is when the observable itself is nonlinear, a nonlinear functional state. You can define these phi1 to phi d, where that is the dimension of the linear system now, as principal eigenfunctions And as I said before, you can get all the other eigenfunctions from these D ones, and your expansion is predicated, which now is infinite. So the expansion or the evolution in time of a vector observable is now infinite, but it really contains products of a finite number of principal eigenfunctions. So, and this is a very general theme in Koopman operator theory. If you find principal eigenfunctions that are associated with an attractor, then all the other information flows from it. So in many cases, this is actually a finite dimensional theory, meaning you have a lossless encoder in machine learning terms. If you find phi1 to phi d, you can recover the state just from that information perfectly, if I'm to put this in machine language, right? So these mathematical aspects differentiate Koopman operator theory as a learning framework from, for example, deep learning, where the underlying theory is actually largely lacking. We don't have it. There are a lot of efforts around the world in order to put it in place. And interestingly, of course, deep learning is based on the same operator. If you think about it, the layer-to-layer operation in deep learning is a composition operation. By the way, that's why it works so well. This is a side comment and maybe a little bit cryptic. So if anybody would like to discuss that after the talk, I'm happy to do it. But that's why it's so efficient as a functional approximation. But here we have a very precise theory. I literally just gave you a theorem that says that that I can have a lossless autoencoder of a nonlinear system that that is of a nonlinear observation on a linear system, you know, that is of the dimension d, which is the dimension of the linear system itself. So here is the point. Knowing n eigenfunctions, we get all of them. I've tried to put this in the encoder terms. So another important thing that you can do with this theory is understanding of which systems are similar, or whether you're observing the same system using, you know, a few different observables. This is important in the context of data fusion. Let's say that you're observing a system with a set of variables x and a set of variables y. And x is governed by some dynamics f of x, and y dot is some g of y. They have the associated flows t for y and s. So you could show that the two systems are practically the same. They're the same evolution if you found a mapping h from one system to another, such that if you apply h to the evolution of x, you get the evolution of y applied to h. It's a commutative diagram. It basically means here is the x system, here is the y system. The x system flows forward, the y system flows forward. If you map x by h and then flow forward by y, it's exactly the same as mapping forward by x and then flowing by h. So the two systems are basically doing the same thing. And a nice little proposition that we proved some years ago says that gives the condition under which this is true using some classical dynamical systems theorems. It says that you can find that diffeomorphism under the condition that, for example, Hartmann-Grobman theorem locally holds. A bigger picture story is that the eigenvalues of the Koopman operator, which in this case are connected to local eigenvalues close to the fixed point, if you find that they are the same for two systems, then those two systems are connected by a simple transformation. They're just an image of each other and not different systems, really. This is the whole notion of conjugacy, which, as I said, can be, and we did with with joint work with Yanis Kavakidis and others, used in data fusion. Now, nonlinear systems, so the first nonlinear thing that I did is I took a look at linear system with nonlinear observables. But here I have a general nonlinear system, and you see now that the expansion is very similar. How so? It is something that looks like eigenvectors in the linear systems. These are really modes. S1 to Sn are principal eigenfunctions of the operator that can be obtained by conjugacy from the linear system. These are the powers, k1 to kn. And then the evolution is really the time evolution multiplied by this eigenvalue integer combination. So you multiply the first eigenvalue with integer, second, and so on. So again, if you know S1 to Sn, k1 to kn are just integers. Lambda 1 to lambda n are eigenvalues of a finite linearization matrix. And then you get a global expansion that looks something like this. And you have to be a bit careful, because when you have expansions like this, they are power expansions, right? They almost look like a Taylor series in this part here. And so there could be analyticity breakdown, and that happens in numerical methods. Page and Kurzweil had some really nice papers on this, where they discovered that, yes, the expansion does hold, but of course it breaks down numerically because of the analyticity properties of the underlying evolution. So again, the theoretical aspects come into picture very strongly, but they help you because you can understand where the numerical analysis is solid and where it can potentially break down. The next step up in complexity after fixed point systems are systems with limit cycle. One of the most famous ones is this so-called van der Pol oscillator. The first two equations, if you neglect the nonlinear term, is just a harmonic oscillator. X1 dot is X2, X2 dot is minus X1, right? This is a nonlinear damping forcing term. So mu X2 is really a forcing, and then mu X1 squared X2 with a minus is a nonlinear damping. The balance of the forcing and damping interacts in such a way that the system has a periodic limit cycle. So the forcing and damping, when their average over a cycle is equal, they balance each other, and you end up in a perpetual oscillation. Such systems can be transformed not in the y dot is a of y form, but something similar. Y dot is a of sy, where s is a variable in a circle and spins continuously. So if you find eigenfunctions for this, you will find eigenfunctions for the whole system. And that, again, is helpful. Here is the general expansion for 2D systems, limit cycling 2D systems. And then in the next slide is the general expansion of limit cycling in n dimensions. And you see the same kind of a principle. There are products of principal eigenfunctions. Then there are eigenvalues, and eigenvalues consist of some integers times the basic exponents of the linearization around the attractor and on attractor evolution. So there is a very general picture of what happens in the coherent part. Remember the splitting, spectral splitting into the coherent part, which is oscillating, decaying, growing. So that was a coherent dynamics. And then the continuous spectrum part, which is chaotic dynamics. So we have in Koopman operator theory a way of splitting the coherent parts of dynamics and continuous part of dynamics. And by the way, just as a side comment, I'll make a number of references to machine learning in this context that helps with not having overfitting, because the noisy part is separated out in the continuous spectrum, and that's the part you don't want to learn using eigenfunctions. In fact, eigenfunctions for such systems don't exist. So you're not doing overfitting when you actually represent the system using eigenfunctions, for example. You will not want to represent the continuous spectrum part of the system using some coherent, approximation. And as I'm sure you all know, that is a serious problem in deep learning in general. So here is the eigenvalue plot, and this is very general for the coherent part. It's basically a lattice. This, for a stable system, the lattice of eigenvalues lives in the left half plane. So the point I was making before is if you measure, remember all of this is available from data. So if you measure system 1 and then measure again with other observables, and you obtain the same spectrum, you know you're measuring the same system. Or if you want to fuse the data, this is a good check that your data is actually coherent. All right. So as I mentioned, one of the interesting applications here, and by the way, how much time do I have at this point?
You have 10 minutes.
Okay. So I'll go into applications here. So that's I think going to be enough. I'd like to show you one that we've done very recently. One of the interesting applications here, of course, and field that's getting more and more attention is application of this in the context of control systems. So now, of course, besides your variables x, you have u, which is the control, and u lives in its own space. In this case, we set it as Rm. You can write this control system as a dynamical system, actually, if you propose dynamics for u. So u has its own dynamics represented by this map S. You can envision it as just having a sequence of control inputs and just shifting them to the left, and then picking on the input at exactly position 0. The point that I want to make is that, in fact, there is a way by which a control system can be considered as a dynamical system of the type that we call skew product systems. And this is joint work with Milan Korda. There is some prior work on control using Koopman operators that is also listed here. Okay. So now we have the data at time t, the data at time t plus 1, and then we know there is some dynamics, nonlinear dynamics, that ports the data at time t to time t plus 1. But we're going to look at forming observables. Remember the basis functions, for example, that I mentioned at the beginning in the intro. And we're going to try to minimize the difference between the observations. So these are the observables that you're embedding your state observations with. So for example, you could have chi I and then chi I squared, or sine of chi I, right? Some library, some basis. And then A is the matrix that is the representation, that matrix djk, the representation of the Koopman operator acting on the previous time data. And I'd like to minimize this over all the matrices of a selected dimension. This dimension here is a hyperparameter. So we also are going to ask that our predictor is linear in U. This is actually, in general, the formalism leads to bilinear equations, but so this is an assumption. And the lifting here is very simple. We'll take some library of functions in the state space, and then we'll basically take the control inputs at a specific time we are looking at. So control inputs at the specific time 0. This can be extended, and we just did in some work that we're doing on soft robotics. That because of time, I don't have a chance to present here. But we want to minimize over all matrices A, and so this original problem of calligraphic A can be represented as minimizing over all matrices A and B, such that the observables at the next time, state observables at the next time, minus A observables at the previous time, minus B times control inputs is a minimum. So that's the idea. So here is the algorithm. You take the X data, the data at the next time, the inputs, you lift it, you formulate the least squares problem, and then the least squares problem has, of course, the standard solution using Moore-Penrose inverse. And then you get a linear system. Well, it's a linear system that's possibly of much higher dimension than your original nonlinear system, but it's still a linear system, and you can design controllers based on linear control ideas, as we did in this Automatica 2018 paper. You can use a variety of things. We used MPC. LQR has been tried. In the meantime, H infinity has been tried. It's interesting to look at, what the local linearization would do. So see, blue is the true evolution, dynamical evolution of the pendulum. Green is when we locally linearize around the fixed point, and then red is what you get with this Koopman type predictor in time. It solves a convex quadratic problem, so it's reliable and fast, and it's completely data driven. There is no underlying model that is associated with it. Here is an example that we did. This is a fluid flow. The observations are only done on these X points here. The lid on the top is moving, and so the control is trying to move the lid to get rid of the oscillations. You have all experienced this problem, I think, if you open the windows in your car and you're driving fast enough, and then you get this boom, 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 boom oscillations, right, of the fluid. So it's a lid over a cavity, the flow over a cavity that causes hop bifurcation and fast oscillations. We want to get rid of those. And here is a movie that's going to show you, if you're seeing the vanishing of red and blue, that's the vanishing of the vorticity associated with the oscillations. So when you see it completely white, that means that it's controlled to a state that doesn't have any oscillations. So we got rid of oscillations. What's interesting, the Kukman controller comes up with this really interesting. This is the control versus time. It comes with this really interesting algorithm where you see that the lid is moved periodically. So here is a movement of the lid, here is a movement, here is a movement. And it's very physically natural. The reason being that if you saw the flow here, goes around. So what happens is that as a chunk of vorticity comes up, the motion is opposed to it and just nulls it. So it's very physical in the way it does things. And so this is something I'd like to point out as well. The learning control AI based on Koopman operator theory is very explainable. You can literally look at the matrix that I mentioned at the beginning and understand what the coefficients are saying, who is interacting with who in the function space, as opposed to, and in deep learning, of course, the coefficients are local. And so they don't have any kind of global interpretation. And that's certainly been a problem for interpreting things physically. I tend to say, if you're modeling a physical process, the operator is the physics. And therefore its coefficients are in fact explainable. All right. So the other place where we utilize this is in Power Grid. This is a Northeastern Power Grid with 10 generators. We were interested in discovering invariant sets. In this case, an invariant set, is the stable domain. The color scheme is a little bit opposite to what it should be. The red domain here is stable. And you've seen an instability in simulation of this system on the right. And so the question was, can we use the Koopman operator methods in this space where we have a pretty high dimensional space, 20 plus dimensions, plus hybrid dynamics, to detect invariant sets? It turns out that level sets of Koopman eigenfunctions at eigenvalue 0, in fact, give you invariant sets. This might sound abstract. It's actually very easy to connect to something that I think everybody on the call knows, which is the level sets of energy in a conservative system are invariant sets. So this is the same idea, it's just more general. It doesn't have to be energy. In this particular case, it's an invariant set that is you're looking at the projection on a 2-dimensional coarse-grained variables in a 20-dimensional space. So, a wide extension of the original idea, but basically the same concept. So that's something that we've applied things to. We've also looked at individual modes. This was the use of eigenfunctions. We looked at individual modes in the power grid. This is all collaboration with your Professor Suzuki from Osaka and Professor Hikihara at Kyoto. We looked at the modes, and then the modes evolve, as I pointed out before, in a very simple manner in time. It's one of the advantages of the Koopman operator theory is that it doesn't attempt to represent the dynamics in time with some LSTMs or whatever. It actually says, well, dynamical processes in time evolve, physical processes very often evolve according to oscillations growing or decaying, and that's how it represents them. So you can say, well, if I have oscillating but nonlinear dynamics, maybe I can plot the amplitude and phase of these modes, collect them, and see whether I have any coherence. In power grid, the problem is detecting the coherency of various generators in a distributed network. So here you're seeing the 2, 3, 6, 7, and 9 form one block, and then 2 to 7, 9, and 10 another block. So what should be is that 2, 3, 2 and 3, and 6 and 7 form one coherent set, and that's indeed what happens in the dynamics. So I'm going to close that. I think I'm hopefully just a few minutes over time. I want to leave you with some conclusions. I hopefully described the theory underlying the Koopman operator framework. I stress the importance of eigenvalues and why they're useful, for example, in data fusion, the eigenfunctions to understand the state space aspects, the modes to understand the global dynamics aspects, for example, like coherence in power grid. But what I want to stress more than pretty much anything else in this talk is that it does provide us with a powerful learning framework, even for dynamical systems that are as complicated as the StarCraft game, and even substantially more complicated than that one that we have done in the meantime. So as far as dynamics processes are concerned, while we use deep learning to learn the elements of the Koopman representation, that's a nice and that's a nice set of, there is a nice set of works out there that speaks to that. So we're not shying away from using machine learning as a functional approximation aspect of this. It does seem that its explicit treatment of time as a separate, as a separate dimension, its explicit treatment of time evolution and its inherent, automatic understanding of the underlying dynamics gives it an edge over other approaches to dynamical systems learning today. And that's what I'm close with, and see whether there are any questions to follow. Thank you.
Thank you. Thank you so much for the great talk, Igor.
Absolutely.
Well, you're right on time. You didn't go over time. It's 11 a.m. We usually go, later than 11 a.m. Okay, so let's have a Q&A session from Gabriel. Could you elaborate on your earlier point about function composition and the efficiency of the deep learning?
Can you help me read that?
Gabriel Ulf. Yes, could you elaborate on your earlier point about the function composition and the efficiency of the deep learning?
Right. Okay, so this is really an interesting question. So when you take a look at the Koopman operator evolution, it's also governed by composition. So for example, your observable gets composed with the mapping T in the first step. And then in the second step, you compose twice with the mapping T. And then in the third step, thrice, right? And if the dynamics is sufficiently complicated, the original function, however smooth it is, it could be something like as simple as a sinusoid, on an interval. If your mapping is something like x prime is 2x mod 1, something chaotic, the features that function f after many iterations is going to have are very arbitrary and can represent, pretty much any point on the unit interval. What I'm trying to point out is that the composition itself is a very efficient way of creating new information from old, provided that the underlying operator is rich enough. And deep learning provides us with operators. Of course, it's a little bit different because it's layer-to-layer dynamics of composition can be different because layers could be potentially different. But the reason, in my view, why it's so efficient and could be potentially exponentially efficient, as the Koopman is that provides this richness of information from layer to layer. I hope that answers the question.
Okay, that's great. Next question is from Ilan Joseph. Thank you for the great talk. Real world systems usually have a chaotic dynamics. Can you say more about the treatment of the continuous spectrum? Yes.
Great. Again, thanks for that question because it follows up very closely on the decomposition that then I end up talking about modes and eigenfunctions, which is used most today. There is this part that's called that is the continuous spectrum that you can specifically decouple from the coherent part. We've developed ourselves methods to extract coherent, I would call them pseudo eigenfunctions from continuous spectrum. I can send you the paper if you're interested, using a class of methods that don't exhibit the operator. So these strictly spectral, basically related to weighted time averages along trajectories. So we don't need to exhibit the matrix itself. So that's one way of getting them. So there is coherence in the continuous part of the spectrum. You might have pseudo eigenvalues, pseudo eigenfunctions that are there. And so I'll leave it there maybe at the intuitive level. Dmitry Giannakis' group at NYU has also discovered some of these elements using compactification methods and kernel methods. So those are the two sets of papers at this point in time that I'm aware of that deal with it. I just got on my screen yesterday another paper from a Cambridge-Cornell collaboration that also deals with it, but I didn't have a chance to read it yet. So I'll have a little bit more when that happens. But Ilan, if you're interested, send me an email and I will just send you the papers.
Great. I'm very interested. Great, Joseph. I'm very interested in continuous spectrum also. Some of the data we get from the earthquake simulation, it has a continuous spectrum. So yeah, I will email you after that.
Me too. On the analysis side, I think this is the most interesting remaining part. So I advocated a lot for control and I advocated quite a bit for learning. But there is one item that we still need to know more about, and that I grappled with from 2005 paper where I proposed a way of treating the continuous spectrum. And now we have even certainly better ways and clearer thinking, but more work needs to be done, and more applications need to be looked at in this sense. Too often, this is just swept under the carpet. People just say, "Oh, let me assume I have an expansion that doesn't include continuous spectrum."
Yeah.
That's a big assumption.
Yeah, it is. All right, another question from Sam. Can we say the Kunman operator is more general version of SVD or PCA? What is the advantage of using Kunman operator?
So a quick answer is no. It is not a more general version of SVD and PCA. They're completely different, in fact. SVD has to, so Koopman operator in principle is not self-adjoint. What one does in SVD or PCA for that matter is it symmetrizes whatever non-self-adjoint matrix is and provides a spectral decomposition of that symmetrized version. Information is lost for a non-self-adjoint operator if you do that. Even if you have a self-adjoint operator, there are advantages of applying the Koopman operator framework, in the sense that you get a strict dynamical evolution using eigenvalues. So a specific example is in fluid mechanics, where SVD or PCA is called proper orthogonal decomposition. When you analyze a fluid dynamics flow using that, you get spatially orthogonal modes. And then the dynamics, the time dynamics, can be very complicated. The Koopman decomposition is orthogonal in time, not in space. And for a dynamical systems person, if you take a look at the simplest dynamical system in 2D, let's say x dot is AX with some matrix A, which is 2 by 2. The decomposition that a dynamical system person is going to do is going to be the eigenvalue decomposition that I showed, which is the dynamics is going to present it as e to the lambda 1t v1, which is the eigenvector number 1, plus e to the lambda 2t v2, which is eigenvector number 2. The eigenvectors v1 and v2 are not in general orthogonal. Those are the spatial components. And we wouldn't want it any other way, because orthogonalizing messes up the time dynamics. So this is actually a very important question, because it points out why the Koopman operator framework is so effective in modeling the dynamical processes. It has the right attitude towards time. I hope that answers the question.
Okay, that sounds good. Well, that brings me another question from my side, but let's go over other people's questions. The Bedros asked, Bedros asked, is your Kuhman mode decomposition different than what DMD or its newer variants can do? Or where is SVD hidden in your scheme? After all, DMD is strictly SVD based.
This enables me to clarify quite a bit further. DMD that Peter Schmidt invented completely independently of the Koopman world is in fact in certain situations related to Koopman operator theory, and in fact provides a numerical algorithm for finding the eigenvalues and modes of the Koopman operator. So let me just summarize this. DMD is one of the many now, but the dominant one, ways of approximating the Koopman operator. The way SVD is used in DMD is to provide a basis. Remember F1, F2 to Fn, those bases? So you start with a certain basis that is given from whatever data you have. You then use SVD there to find another basis that hopefully contains more information and coarse-grained information. So that's how SVD is used, basically for coarse graining in DMD. I do have to mention this is an idiosyncratic point of view. I'm explaining this from a perspective that's described in my paper, Numerical Analysis of Koopman Operators. It's on archive, so Bedros, if you want, I'll send it to you. But and Bedros is saying, what does SVD do to the continuous spectrum? In general, it kills it, and that's why when you do want to address the Koopman operator decomposition or Koopman mode decomposition in its totality, we really need to go beyond DMD. One of the ways of doing this is just the reason SVD was introduced by Peter, brilliantly into DMD, was to make sure that the numerics is in fact robust, right? So that the conditioning of the matrix is correct. So it was really a numerical approach, very, very, very nicely done. But it does something when you something that is not necessarily good when you think of it in context of Koopman, and Bedros just pointed out in no unclear terms. That is a problem. We had some papers with Zlatko Drmac from Zagreb. It is really his algorithm, the Vandermonde-Cauchy approach that deals with the same problem without really cutting things off. And this might be another way forward. But by now, there are 3 different ways forward on continuous spectrum. So I'm quite hopeful that in the next couple of years, we're going to have a very robust set of ideas on how to compute and how to make sure we're not missing anything.
All right, great. The next question from Ilan. A finite dimensional approximation of the Kuhman operator can only have one attractor. However, a dynamical system might have more than one attractor, which leads to bifurcation phenomena. Does this limit the applicability of the model for studying bifurcation dynamics?
Great question. I'll start with a simple answer. No, it doesn't limit. For any dynamical system with however many attractors it has, the Koopman operator does contain all the information about all the attractors. So you can basically recover the dynamics perfectly if you know the operator perfectly, right? So then the question comes to what has been done in this context and have people looked at it. So what's really interesting is that whenever bifurcation happens in any part of the state space, the Koopman operator is going to have some eigenvalues that have 0 real part. So you can certainly study bifurcations in the context of the Koopman operator itself. When you look at the problems in which there are transitions between different attractors, that's also very interesting. And on the simple expansions, like I did, well, maybe complex in theory, but relatively simple as because they have a form of Taylor expansions, just in terms of eigenfunctions, can fail because of analyticity properties. That was the paper of Page and Kurzweil that I mentioned. And in that case, on the numerical side, one needs to be really careful, and people are working on that as well as we speak. I should say that besides continuous spectrum, this is also a really interesting theoretical and question what the analysis can advance further. But interestingly, at the bifurcation points, you usually have appearance of continuous spectrum as well, so the 2 are connected. Thanks for that question. Great question.
Okay, great. Okay, next one is not a question, but it's a comment by Rob Blake. Orthogonal in time seems to be the takeaway, I think. So related to that, I have a question. I have my own questions. Going back to the SVD. So let's say you have a simulation data, and you apply the SVD to get, for example, POD modes from the flow data you have, flow dynamical data you have. The left singular matrix from that SVD decomposition holds a spatial, the modes. But if you look at the right singular matrix, it does hold a temporal modes corresponding to each spatial mode, and that describes a temporal modes of the, the individual spatial modes, how it behaves, etc. And you could extract those right singular matrix and then combine them so that it's orthogonalized and come up with a orthogonal temporal basis of individual the spatial modes. So it doesn't describe the whole, it doesn't go into the temporal modes directly, but it goes through the spatial modes. So maybe, so there's some connection between the Kuhman operator and the SVD in that sense.
There is a little theorem that you can prove. I never published it really. That describes precisely when the POD modes or proper orthogonal decomposition modes or PCA, and Koopman modes are the same. And that's in the case when you basically have a linear system or a linear representation, and the modes are normal. There are a large number of works in which some kind of combinations are pursued of the two. I would say the first thing to try any new method on is literally the problem that I mentioned with a linear system, 2x2 matrix, and non-orthogonal eigenvectors. And one immediately sees how much more complex is to do PCA, or rather understand what the system does in the PCA representation rather than in the Koopman representation. In the Koopman representation, it is basically the same as what we know. It's an eigenvector expansion. The PCA representation mixes the eigenvectors, and that, to me at least, I've been trained in dynamical systems, so to me, that mixes things up. The place where the place where the PCA comes from really is from analysis of stochastic processes, in which orthogonalization in space is a very desirable property. And I've myself argued that, for example, aspects of continuous spectrum that have no features, like there are no pseudo eigenfunctions or anything like that, you could effectively use the POD on. Actually, in the original paper on Koopman mode decomposition in 2005, if you take a look at the last section and conclusions, it says precisely that. But that's the situation in which you have no coherent part. Anytime there is a coherent, and one needs to extract that, anytime there is a coherent part, in my view, applying the POD before you've extracted the coherent part is going to confuse things up, dynamically speaking.
Got it. Okay. Thank you so much. Yeah, I don't think I have any more questions except the Rob comment out. I think that would make sense. It would be equivalent to saying all eigenvectors are orthogonal if your linear system is symmetric. Yeah.
Yeah. So in that case, it's the two methods end up being the same. You can prove it. It's not very hard. But I never published it. Probably I should have. Maybe I should publish it just as a little note, because it would clarify some of these questions. But my remark stands, right? So when a dynamical system has coherent features and the eigenfunctions are not orthogonal, then probably the Koopman framework is the efficient one to go with.
All right. Okay, sounds good. I don't see any more questions. Well, we have like 20 minutes past the 11, but we usually do, so don't feel bad, Igor. It means a lot of people are interested in your work. And well, let's thank Igor. It was wonderful talk, and I think a lot of people appreciate it very well. Thank you so much. Let's thank Igor for the speaker today for the wonderful talk and wonderful Q&A session.
Thank you so much for having me. I really appreciate it. Some great questions.
Yeah. All right. With that, let's conclude. Except Ilan said if the linear system can be presented as a normal matrix, a dagger equals 0.
I was just commenting on the last comment, just that's the condition for which the eigenvectors become orthogonal.
Practically, yes.
Yes. All right. Sounds good. All right. Shall we finish up? Thank you. Thank you so much. And keep in touch, Igor. And I need your what is it? The PDF.